I have a tip for you. This chapter is in many ways a repeat of the previous chapter. So if you keep in mind that what you learned about the z-test will apply to the t-test, you will find this chapter easier to learn. In the last chapter, you learned your first inferential test statistic called the z-test, for use when the population standard deviation sigma is known. In this chapter, you're going to learn your second inferential test statistic called the t-test. We use the t-test when sigma, the population standard deviation, is not known, but the population mean is known, or at least it is hypothesized. In fact, only rarely is sigma known, so we will be using the t-test more than the z-test for single sample research studies. The t-test for one sample has several types of application. One application mentioned in the Cronk SPSS textbook would be to see if the current set of weather data is showing a change from long-term weather patterns. For example, is global warming occurring? We could take an average of the Earth's temperatures over the last 10 years and then compare that to the average temperatures in the preceding 100 years. The 100 years would be considered the population, and the last 10 years would be considered our sample. So we would subtract these two mean temperatures from each other, divide by a calculated standard error of the mean, and decide whether the last 10 years average really is a significant difference from the last 100 years, or whether it is just the kind of variability that had occurred anyway over the past 100 years. Another example of using a t-test would be in the production of things that have to weigh a certain amount. For example, food packages weights. We might be interested in seeing whether or not 1 pound packs of hamburger in stores really weigh 1 pound. Now we know there's going to be some slight under or overweight from package to package, but we can take a random sample of several packages from a number of different stores and compare the mean weight of those packages to the population's hypothesized mean weight of 1 pound. The t-test can tell us whether or not there is a statistically significant difference between the two means. These are the formulas involved in calculating the t-statistic. First, look at the blue box on the far right side of the slide. This is the formula for the t-statistic. Notice that it is very similar to the z formula from the preceding chapter. The main difference is that in the denominator we have little s sub m for the standard error of the mean instead of sigma sub m. The reason for that is that we have to calculate the standard deviation from the sample data when we don't know the population standard deviation. We begin our calculations with the formula in the yellow box at the upper left of the slide. This is the sum of squares formula that you learned in Chapter 4. We insert the calculated sum of squares in the formula in the green box below. This is the formula for variance that you learned in Chapter 4. Moving to the right to the formula in the lavender box, we take the calculated variance, s squared, and plug it into the formula in the lavender box in order to calculate the standard error of the mean. Last, we take the standard error of the mean, s sub m, and plug it into the blue box formula in order to calculate the t-statistic. Notice that the only difference from the z-statistic that you have calculated before is that s sub m on the bottom of the t formula came from formulas that used s instead of sigma. Note that the extra green and lavender colored boxes contain equivalent formulas, which you've seen before, for calculating the standard deviation, which is the square root of the variance. The t-statistic formula looks similar to the z formula, but because the t formula's denominator, that is the s sub m, varies based on sample size, we need a family of t distributions rather than the z normal distribution. You can find that family of distributions in table B2 on page 588 in the textbook. This is the table we use to find the critical value for hypothesis testing with the t-statistic. For a given hypothesis testing problem, the correct table row to use is determined by the degrees of freedom in the problem, defined as n minus 1, which is the number of subjects or participants minus 1. The correct table column to use is based on the alpha level we've chosen, which is typically 0.05, but could be other values, depending on how conservative we want the statistical test to be, or depending on whether we are looking at a one-tailed or a two-tailed hypothesis. Let's see how to use Table B2 with an example of a study that had 3 degrees of freedom in which we are interested in where 10% of the sample means might fall. On the left side of the table, there is an arrow pointing to the 3 degrees of freedom row. This means that there must have been 4 subjects or participants in the study because n-1 would be 4 minus 1 or 3 degrees of freedom. Then reading down the 0.10 column for the two-tail situation, we find the table value for t is 2.353. Looking above in the one-tail heading, you can see that 5% or 0.05 of the sample means would be above a t of positive 2.353 or below negative 2.353. Let's see how this is graphed on the next slide. Figure 9.2 is a graphic representation of the information we found in the preceding table. The 2.353 cutoff point in the upper and lower tails came from Table B2 for a research study with 3 degrees of freedom. It's the cutoff point in which 5% of the possible sample means fall into the upper tail and 5% fall into the lower tail, or 10% in both tails combined, the two-tail situation. Figure 9.3 is a reminder of the basic logic of hypothesis testing. I also want to talk about this figure because the way it is labeled can lead to some confusion. It may seem like a whole population is treated, but what we are actually doing is treating just the sample taken from the population. On the left, we have a known population before treatment. That is, we know that it has a mean of 30 on whatever we are interested in measuring. Then we do something called the treatment with the participants. We want to know, if we treated the whole population, what would the mean be after the treatment? So on the right in the graph of the unknown population after treatment, the mu equals has a question mark. Of course, what we actually do is we take a sample, treat the sample, and assume that the mean of the treated sample will represent what the mean of the whole population would have been if we had treated the whole population. Keep in mind that what we are really doing is treating a sample rather than treating the whole population. Since the textbook goes through this example of newborns' preference for attractive faces in detail, what I'm doing here is just summarizing to remind you of the 4 steps of hypothesis testing. I will go into more detail about calculations when I get to my own example later. Step 1 is to state your hypotheses. The null hypothesis, H sub 0, states that the mean time looking at the attractive faces would be 10 minutes or half of the 20 minutes the newborns were observed. In other words, the newborns won't have any preference for one face or the other. They will spend 10 minutes on average looking at each type of face. The alternative hypothesis, H sub 1, states that the mean time looking at attractive faces will not be 10 minutes, that in fact the newborns will spend more time looking at one type of face or the other. Step 2 in the hypothesis testing is to find the critical value from the table of t. We first need the degrees of freedom. In this case, because we are testing 9 newborns, the degrees of freedom are 9 minus 1 equals 8. We will use alpha level of 0.05, which is typically what we will use in examples throughout the course, unless stated otherwise. And we have stated a two-tailed hypothesis, which is typically what we will use rather than one-tailed, unless stated otherwise. In Table B2, which is reproduced on the next slide, we look in the 8 degrees of freedom row and in the two tails 0.05 column to find the critical value of plus or minus 2.306. Step 3 involves calculating t in 4 stages. Stage A is to get the sample mean. In this case, the mean is 13, and the sum of squares, which is 72. We then use the sum of squares value in stage B to get the sample variance, s squared, which equals 9. In stage C, we get the estimated standard error of the mean, s sub m, which equals 1. Last, in stage D, using the t formula, we subtract the null hypothesis mean of 10 from the sample mean of 13 and divide by the standard error of the mean, 1, to get a t-statistic value of positive 3.0. Again, the book shows you this in detail if you weren't able to follow the calculations verbally. In step 4 of hypothesis testing, we make a decision. Does our calculated t beat the table? That is, does the t we calculated of positive 3.0 fall in the critical region, thereby making it a rare event if the null hypothesis were true? If we beat the table value, our result will be statistically significant. And yes, our calculated t does beat the table value of 2.306. We have a statistically significant difference in looking time with attractive faces looked at longer. Figure 9.5 summarizes the cutoffs for the experiment that we just described regarding newborn face preference. This is the t-distribution for 8 degrees of freedom. We see the cutoff point of 2.306 in the upper tail and negative 2.306 in the lower tail. Because our calculated t was positive 3.0, it falls into the blue region of the right-hand tail. That is, the mean of that sample is unusually high for a null hypothesis that claims there really shouldn't be any difference between the means. Therefore, we reject the null hypothesis and say instead that there is a significant difference between the two means. The newborns do spend more time looking at attractive faces. Before I go through my t-test example, I have a couple of tips to keep in mind when you're working problems on your own, either at the end of the chapter or on the exams. The first tip to remember is that the formulas are summarized for you on the back inside cover of your textbook. Often in the problems in the textbook or on the exam, you will be provided with some of the preliminary values so that you don't have to always calculate from the raw data. For example, the sum of squares and the variance is often given to you. The reason for this is that after you've proven that you can do these basic calculations in earlier chapters, there's no need to keep having you do these calculations over and over again. Instead, the focus can be on the new formulas you are learning, or on how to select an appropriate statistic, or how to interpret the results once they are calculated. The third tip is that the formulas will tell you what you need. As you look at a formula, it will tell you what you have to do before you can complete that particular formula. Go back 9 slides to review the formulas in colored boxes. In the t-test formula, it reads t equals m minus mu over s sub m. You'd want to calculate t, but when you look at the formula, you realize that you only know one of the required values, the mu. The mu would be given to you. That is the population mean that you're comparing your sample mean to. So the t formula tells you that you have to calculate m, which will be an easy calculation of the mean of the sample. The t formula also tells you that you have to calculate s sub m, the estimated standard error of the mean, which moves us to the left in the formula slide. Having moved left to the formula for the standard error of the mean, we now realize that we don't have s squared, although we do have the n. So that brings us back one more formula to the left to the formula for the sample variance. In that formula, we could easily figure out n minus 1, but now we see that we also need the sum of squares. So now we move back to the very first formula on the slide, the one with the yellow background, to calculate the sum of squares. So if you're doing a problem in which you need to find t, but don't have a clear idea of where to begin, just think backwards from the t formula, and eventually you'll find that you need to begin by calculating the sum of squares from the raw data, then the variance, then the standard error of the mean, and finally the t. Of course, as you become familiar with calculating the t-statistics, you will probably know how to begin the sum of squares, etc. But if you get stuck, remember to let the formulas tell you what you need to do. And do read problems carefully to see what's already given to you, such as the sum of squares or the variance. After I overview the example on this slide, I will show my handwritten solutions on the next slide so that you can get experience seeing how I would write down the problem if you were sitting in the classroom watching me write it on the chalkboard. I hope this type of addition to the PowerPoint slides is useful to you and makes up somewhat for not being able to see this done in a classroom setting. This example supposes that the government has mandated that mid-sized cars get 45 miles per gallon of gasoline. The question is, does the following random sample of 6 Toyota cars' gas mileage indicate the company is in compliance or not? We see here a random sample of 6 cars with various miles per gallon performance, 40, 44, and so on. Just a reminder that in an actual study, we would have many more cases than 6. We go through the same 4 hypothesis test steps you saw in the preceding example on newborn face preference. The first step is to state our hypothesis, both in symbolic form and in plain English wording. After we've done that, we determine the alpha level, degrees of freedom, and number of tails for entering the t-table. Then we calculate t from the sample data. The last step will be to interpret the calculated t by comparing it to the critical value obtained from table B2, the t-table. In our written interpretation, we will include terms like t, df, alpha, p less than or p greater than, two-tailed, and significant or non-significant. We will also want to use plain English terms regarding whether the company is in compliance or not. Here is the solution for the gas mileage problem regarding whether Toyota is in compliance or not with the government standard of 45 miles per gallon. On the right side of the slide is my handwritten solution, which is like what I would write on the chalkboard if you were sitting in a typical classroom. To be sure you are reading my handwriting correctly, I have typed on the left side of the slide the results of the various calculations. Looking at my handwritten example, starting at the top, you see that I've written the null hypothesis and the alternative hypothesis. The null hypothesis states that mu is equal to 45 miles per gallon. In other words, there won't be any difference in the sample mean compared to the population mean. The alternative hypothesis, H sub 1, says that mu will not equal 45 miles per gallon. I'm going to work through the problem in a way that will be suitable to either a two-tailed or a one-tailed test, emphasizing the two-tailed version because the hypothesis is written that way. In other words, with a two-tailed test, we are also allowing for the possibility that Toyota beats the federal standards. But we can also do a one-tailed test. I'll explain that at the end of the problem. The next step is to write the data down in column form so that you can easily work with the original x scores by squaring them, which is done in the second column. At the bottom of each column I have written the sums. The sum of the original x scores is 258. The sum of the x's squared is 11,118. This is also a convenient place to write down the mean, 43. I've noted on the side margin the number of cars, n equals 6. And because the initial steps in the hypothesis testing involves getting the table critical value, you might want to look down to the lower left where I've calculated degrees of freedom, n-1 or 6 minus 1 equals 5 degrees of freedom. I have also written down two-tailed and alpha. I have chosen to test at the 0.05 level. Taking that information to the table of t, I found a critical value of 2.571. On the next slide, you can see how I got that value from the table. Also notice that I carry out answers to 4 decimal places. This is a reminder that in the intermediate steps of a problem, you should carry out 1 more decimal place than what you eventually want in your final answer. Since I want to get t with 3 decimal places, the intermediate steps should have 4 decimal places. This will give me a level of precision that is necessary, but I don't need to go more than 4 decimal places. Okay, with these preliminaries, let's go back to the upper right part of the sheet where I have written the formula for SS. We will be going right down the right side here, calculating each of the formulas that we need. Recall a few slides ago that I said if you don't know how to start, let the formula tell you what you need? Eventually, that process leads you back to realizing that you need to start by calculating the sum of squares, or SS, then the variance, then the standard error of the mean, and finally the t. Notice that I circle answers so that I can more easily find them for use in later formulas or for rechecking my calculations. Having calculated t, we now compare our value of negative 2.236 to the table critical value of 2.571. Actually, negative 2.571, since the tables don't redundantly put in values for the below the mean part of the distributions. The game is to try to beat the table. If we don't beat the table, we do not have a significant difference. In fact, we did not beat the table with this two-tailed test. Our t calculated is less than the critical value t. Therefore, we have a non-significant difference between the Toyota sample of 6 cars getting 43 miles per gallon and the government-mandated 45 miles per gallon. That difference of 2 miles per gallon is not statistically significant. According to this result, we have a difference that is just due to sampling error. Notice in the extreme lower right corner of the handwritten sheet, it says P greater than 0.05. I'm introducing this terminology here because we will be using it a lot from here on, and it is the standard way of writing that we didn't get significance. The probability is greater than 0.05 that the finding is just due to chance. Now, what if we had done a one-tailed test? If we had done that, we would have found that there is a significant difference. That is, that the 42 miles per gallon is significantly less than 45. I'll explain the reason for that with the table on the next slide. This is a copy of Table B2 from the back of your textbook, the table of t-values for the t-distributions. I've added some arrows and circles to the table regarding the car mileage example. First of all, on the left side of the table, I've drawn an arrow at the 5 degrees of freedom row for our car mileage example. Then at the top of the table, I've drawn arrows to the 0.05 alpha level I had chosen for either a one-tailed test or a two-tailed test. The null hypothesis we used in this example is that the gasoline mileage would be neither below nor above the government standard, and we did a two-tailed test. However, some would argue that we should have done a one-tailed test if we were pretty sure that the difference would be only in one direction, either that Toyota would never build low-mileage cars or that Toyota cheats in some way. But in this case, I thought that we needed to test for both possibilities, hence a two-tailed test. And as discussed in the previous slide, the two-tailed test was non-significant since our calculated t of negative 2.236 did not beat the critical table value of 2.571. Let's look, however, at what the result would have been if we had done a one-tailed test. Looking at the 0.05 column in the one-tail section for 5 degrees of freedom, we find that the critical table value to beat is 2.015. Our calculated t of negative 2.236 beats that value. Therefore, with a one-tailed test, we would have found a statistically significant difference, and we would have concluded that Toyota's cars were not meeting the government standard. However, if you had originally done a two-tailed test, it would not be appropriate to change to a one-tailed test in order to be able to report a significant finding. The explanation for that restriction is a bit too complicated to get into here. Here is an example of a typical sentence in proper APA format that would be included in a research report. Later in this lesson, we will take a closer look at the components that need to be in such sentences. The Cohen's d you learned about in the last chapter can also be used with t-test results. A t-test determines whether or not we have statistical significance, but Cohen's d tells us whether the difference is small, medium, or large in terms of standard deviation units. Note, however, that in the formula we now use S rather than sigma, since we are working with a sample, not the whole population. To interpret the calculated Cohen's d, we again refer to Table 8.2 on page 233 in Chapter 8, which is reproduced on the next slide. By comparing our calculated Cohen's d to the values in Table 8.2, we can determine whether a statistically significant result is small, medium, or large. You might have some difficulty in deciding whether to call a Cohen's d small, medium, or large when it falls between the three listed values. Since these values are not precise cutoffs, I suggest going with whatever value the Cohen's d is closest to and use terms like small to medium if the value falls near the middle between two values. An alternative measure of effect size is to calculate R squared, which shows the percentage of variance explained in the t-test. This test was also developed by Cohen and is more commonly used than D. The conceptual formula is the variability counted for divided by the total variability. The computation formula squares the calculated t from the t-test and divides that by the sum of t squared plus the number of degrees of freedom used in the t-test. To interpret the calculated r-squared, refer to Table 9.3 on page 265, which is also reproduced on the next slide. Table 9.3 lists three values of r-squared, representing small, medium, and large effects. As suggested earlier, it might be difficult to decide whether to call an r-squared small, medium, or large when it falls between the three listed values. Since these values are not precise cutoffs, I suggest going with whatever value the calculated r-squared is closest to, and use terms like small to medium if the value falls near the middle between two values. In addition to explaining what the textbook tells you about reporting the results of a t-test, I am also going to give you a table to help keep track of what the different terms mean. As you know by now, when you calculate your t, you need to compare it to the critical value from Table B2 at the intersection of the degrees of freedom row and the alpha level column. Once you have determined whether your calculated t beat the critical value or not, the table on the slide shows how each of the various terms relate to one another. I hope this table helps you sort out when to use the terms significant, not significant, less than, greater than, reject, and retain. I've listed an alpha level of 0.05 in the table, but you would substitute 0.01 or whatever other alpha level was appropriate for the particular research study being analyzed. If your calculated t beats the critical value, then all of the terms in the left-hand column would go together. Beating the critical value means that you reject the null hypothesis. You have a statistically significant result with the probability less than 0.05 of having made a type 1 error. That is, the error of thinking that you have a real difference when you don't. If your calculated t does not beat the critical value, then all the terms in the right-hand column would go together. In this case, you fail to reject. That is, you retain the null hypothesis. You do not have a statistically significant difference between the means because there is a greater than 0.05 probability that the difference between the means is just due to chance sampling error. The last section of the slide lists the components of sentences for reporting the results of t-tests. As we'll see on the next slide, there are a number of ways of combining these components into one or more sentences for reporting your findings. The important thing is to include all the components in some way. You need to include wording that describes your group or groups, such as the group labels or the name of the treatment done to the groups. I'm using the plural groups here because these guidelines also apply to research in which there are more than one group, such as in the next chapter on t-tests comparing two different treatments. It is also important to use wording that indicates what was measured, that is, what were the data. Include the sample mean, M, and the standard deviation, SD. State whether the results of the t-test were significant or not. Finally, write the technical information, which includes the calculated t and its degrees of freedom in parentheses, the p less than or p greater than symbol, whether it was a two-tailed or one-tailed test, and Cohen's d or r-squared. There are several ways to write results sentences incorporating the components listed on the preceding slide. Compare the first example with the version on page 266 in the textbook. Compare the second example with the example back on slide 17. In all four examples, see if you can identify the components listed on the preceding slide. This table summarizes how to write null and alternative hypotheses for directional one-tailed tests and non-directional two-tailed tests. As explained earlier in this course, we will deal mostly with two-tailed tests, where the null hypothesis, H sub 0, states that the mean of the population will remain the same following treatment. The alternative hypothesis, H sub 1, states that mu will not remain the same after treatment. The one-tailed hypotheses are a little more complicated, because H sub 0 will be different depending on which alternative hypothesis we adopt. I recommend writing down first the alternative hypothesis. Then all you have to do for the null hypothesis is reverse the direction of the greater than or less than sign and add an equal symbol. The first version of the null hypothesis reads less than or equal to, and the other version reads greater than or equal to. Here are how the hypotheses for the newborn face preference example from earlier in the lesson would be written for two versions of directional hypotheses. The graph in Figure 9.7 shows the one-tailed test for the newborn face preference example in which we think newborns would look longer at attractive faces. Notice that compared to Figure 9.4 on an earlier slide, the rejection region is larger, making it easier to reject the null hypothesis. If we had made the opposite one-tailed hypothesis, the shaded in tail would be on the left end of the graph. The M&M package counts example is from an exercise I do in my on-site sections of statistics. Here is the problem as I present it to students. A consumers group suspects that the M&M Mars Incorporated candy company makes extra money by putting fewer than the specified 57 pieces in their 47.9 gram packets of plain M&M candies. The data you see are from a previous class that counted the number of M&Ms in 12 packets. Before looking at the next slide that has my handwritten solution on it, try carrying out the appropriate hypothesis test to determine whether the average of the 12 packets in the sample differs or not from the specified population mean of 57. This is my handwritten solution for the M&M exercise, like I would write on the chalkboard if we were in a sit-down class. We start at the top left with our null and alternative hypotheses. The null hypothesis is that the mean will equal 57, because the population mean is stated to be 57 pieces per package. The alternative hypothesis states that the mu will not equal 57. This is definitely a situation requiring a two-tailed hypothesis, despite the fact that the consumers group suspects cheating, because we also want to see if perhaps the M&M Mars company is wasting its own money by packaging too many pieces. The collected data are written down in a column labeled X for scores, and the square of each X is in the column beside. I have summed both columns and calculated the mean because I know I'll need these values in formulas. At the bottom left, I've done the next step in hypothesis testing of calculating the degrees of freedom, n-1 or 12-1, which is 11. And I specified a two-tailed test at the 0.05 alpha level. In table B2, which is reproduced on the next slide, we find a critical t-value of 2.201 at the intersection of the 11 degrees of freedom row and the two-tailed column 0.05 level. Notice again that I'm calculating to 4 decimal places, because I know I eventually want to have 3 decimal places in the final answer for t, since that's how many decimal places are in table B2. On the right side of the handwritten sheet, I wrote down the formulas, filled them in, and calculated. Just a reminder that if you do not know where to begin, look at your ultimate goal, the t formula, and let it tell you what you need. Once the t is calculated, it's time to make a conclusion. First, review slide 24 to remind yourself of the words and symbols that go together for either beating the table or not beating the table. Comparing the calculated t of negative 5.202 to the critical table value of 2.201, we see that we do beat the table, therefore having a statistically significant difference, which means that the M&M Mars company is underfilling their packages. However, I need to make a disclaimer in order to avoid a lawsuit. Remember that I made up the 57 pieces population mean for the purposes of this exercise, so we aren't really claiming that the real-world M&M company is cheating. They actually sell their packages by weight, which is more accurate than counting pieces that might vary slightly in size. In summary, with a calculated t that is in the critical region beyond the table t value, we reject the null hypothesis that stated there would be no difference. We rejected the null because our sample mean fell in a region of the t distribution that would be very likely to occur if the null were true. We stated that the probability is less than 0.05 that the observed difference between the sample mean of 55.6667 and population mean of 57 is just due to chance. Instead, we concluded that it is a real difference. See the sentence example on the bottom left side of the slide. Can you identify the required components that were listed on slide 24?